Now these are some of the equations for the preparation of alkyl halide from alcohol. The first one, alcohol when treated with hydrochloric acid in the presence of catalyst zinc chloride, it is forming alkyl halide. Here in this case it is alkyl chloride plus water. Now since tertiary alcohols are highly reactive, so tertiary alcohols give alkyl chloride when treated with HCl at room temperature. There is no need of a catalyst there, but in case of secondary and primary alcohol, catalyst like zinc chloride has to be used. Next one is alcohol plus sodium bromide plus H2SO4. Now here OH is getting substituted by bromine. So alkyl bromide is formed and byproducts are sodium hydrogen sulfate and water. Next is alcohol with trihalide of phosphorus. Will also give alkyl halide and H3PO3. Here X denotes the halogen like chlorine and bromine. Then again PCl5, pentachloride of phosphorus or phosphorus pentachloride can also be used to obtain alkyl chloride. Byproducts are POCl3 and HCl. Now instead of using phosphorus trihalide directly, combination of red phosphorus and halogen is used along with alcohol, and this gives alkyl halide. Here X2 represents halogens, bromine and iodine. Another method is treating the alcohol with SOCl2. This is known as thionyl chloride. It will give chloroalkane or alkyl chloride, and the other byproducts which are formed like sulfur dioxide and hydrogen chloride. These are in gaseous state and these escape from the reaction mixture, leaving pure chloroalkane or alkyl chloride. Preparation of alkyl chloride is carried out by passing dry hydrogen chloride gas through a solution of alcohol. This is the one method, that is passing dry hydrogen chloride gas through a solution of alcohol, or by heating a mixture of alcohol and concentrated aqueous halogen acid. Aqueous solution of halogen acid is prepared and then it is mixed with alcohol, and on heating this mixture alkyl halide is obtained. Now the above methods are not applicable for the preparation of aryl halides because the carbon oxygen bond in phenols has a partial double bond character. In case of aromatic alcohol, that is phenol, this OH group is bonded to the carbon of the benzene ring. So this carbon oxygen bond has slightly double bond character. Due to this slight double bond character, this bond is strong. It is not easy to break this bond. Therefore, these methods are not applicable in the preparation of aryl halides. Next is preparation of alkyl halides from hydrocarbon. The first is by free radical halogenation. Now in this case alkane, here it is butane, is treated with halogen in the presence of UV light or heat. In the presence of UV light or heat, free radical is generated, means chlorine free radical will be generated, and the product which is obtained, here the product, two products are obtained. One is 1-chlorobutane and this second one is 2-chlorobutane, but along with these some polyhaloalkanes, means alkanes with more than one halogen atoms are also formed, and it is difficult to separate them as pure compound. So the yield of any single compound is low. So in this method, though haloalkanes are obtained, but a mixture of isomeric mono and polyhaloalkanes are obtained, from which separation of pure compound is not possible. Another method is from alkenes. Alkene, if it is treated with hydrogen halide, this hydrogen halide will add across the double bond, forming haloalkane. If this HX, here if this is HCl, then HCl will add across the double bond and chloroalkane will be obtained. If this represents HBr, in that case HBr will add across the double bond and bromoalkane will be obtained or alkyl bromide will be obtained. If HX represents hydrogen iodide, in that case Hi will add across the double bond and alkyl iodide will be obtained. If the alkene is unsymmetrical, means the number of carbon atoms on both the sides of double bond is different, then the addition of hydrogen halide will take place according to the Markovnikov's rule. Here, this hydrogen iodide breaks into H plus and I minus ion. H plus ion goes to the carbon having greater number of hydrogen atoms and I minus goes to the carbon having lesser number of hydrogen atom. This H plus will bond with the carbon having greater number of hydrogen and I minus will bond with the carbon having lesser number of hydrogen. So this one is the major product, that is 2-iodopropane is the major product and the minor product is 1-iodopropane or propyl iodide. This is the minor product. The minor product is the anti-Markovnikov product. Then another method is addition of halogens. For example, bromine in CCl4 is taken and this bromine adds across the double bond to form vicinal dibromide. Here this alkene is ethene. So bromine in CCl4 is taken, bromine adds across the double bond of ethene and it results in the formation of vicinal dibromide. Vicinal dibromide means the bromine atoms are present on the adjacent carbon atoms. Now here in this case, the reddish brown color of the bromine fades. When bromine in CCl4 is added to an alkene, it results in the discharge of the reddish brown color of bromine. Discharge of the reddish brown color of bromine means the reddish brown color of bromine fades. So this helps in the detection of double bond. If a solution of bromine in CCl4 is added to a given compound and reddish brown color of bromine is fading away, then it means that the given compound is having double bond. So this test is an important method for the detection of double bond in a molecule. The addition results in the synthesis of vicinal dibromides which are colorless. So reddish brown color solution of bromine, its color is reddish brown, it becomes colorless. Why? Because now the bromine molecules add across the double bond, no bromine molecules available in the solution, so the solution becomes colorless.